Hello, welcome to the next video lecture on strength of materials.
In the previous video, we had discussed 2D state of stress where sigma x, sigma y, tau xy were the independent stress components. The state of stress can be represented graphically like this. A patch of square area like this. Sigma x will be acting like this, sigma y will be acting like this, and tau xy, shear stress, will be acting like this. We also know how to calculate the normal and tangential stress on an inclined plane like this. For that, we had derived analytical expressions for sigma theta and tau theta in terms of theta. We also know that on any plane, if the shear stress is 0, then the plane is called principal plane. The corresponding stress is called principal stress. Sigma 1 and sigma 2 are the two principal stresses in 2D system. We can calculate the orientation of these principal planes. We called it as theta 1 and theta 2. Here, sigma 1 is called major principal stress, sigma 2 is called minor principal stress. We can also calculate the maximum shear stress and the orientation of maximum shear stress plane, theta tau max. All these we have found out using analytical equations. So this method is called analytical method. But now we will see a graphical method of calculating all these parameters. And this method is called Mohr Circle method. We are using these sign conventions. We know that tensile stress is taken as positive and compressive stress is taken as negative. And the convention for theta, the angle of the plane, is positive when measured counterclockwise. Shear stress is taken as positive when it forms a counterclockwise couple on the opposite vertical faces. Otherwise, it is taken as negative. For example, you observe here in the first sketch, opposite vertical faces, shear forces are forming counterclockwise couple, so it is positive here in the first case. Whereas in the second case, opposite vertical faces, shear forces are forming clockwise couple, so it is taken as negative. Graphical construction in Mohr circle is produced by taking normal stress along x-axis and shear stress along y-axis. This is x-axis, normal stress sigma. Vertical axis is shear stress. But positive shear stress is taken downward. And this is the origin. So this is positive shear stress direction and this is positive normal stress direction. Now we will see what is the procedure for constructing Mohr circle. I have considered the state of stress like this. We know sigma x, sigma y, tau xy, and also a plane which is inclined at theta degree to vertical like this. On this plane, we have to find out the normal stress sigma theta and shear stress tau theta. First step is to draw the y-axis which represents shear stress tau and draw x-axis which represents normal stress sigma like this. This is sigma normal stress and this is tau shear stress, positive downward, and this is the origin. First we have to consider the vertical faces. The normal stress present on the vertical face is sigma x and shear stress present on the vertical faces is forming an anti-clockwise couple like this. So it has to be taken as positive according to our convention. We know that shear stress is positive downwards on the Mohr's plane. First, let us measure sigma x on the x-axis, that is sigma axis, and locate the point. Let us say that point comes somewhere here. Means the distance of this point from the origin horizontally is sigma x. After marking sigma x on x-axis, we have to mark tau xy because we are trying to represent vertical faces now. So if I measure tau xy along downward direction, let us say it comes like this. So this distance is tau xy. So when I consider vertical faces, there is normal stress sigma x and there is positive tau xy. I have represented both. Let me call these points as A here and E here. Now let us consider the horizontal faces, that is the top and bottom face, where normal stress acting is sigma y and shear stress acting is tau xy, which forms a clockwise couple now, which has to be taken as negative. So I measure sigma y along x-axis. Let us say it comes somewhere here. I will call this point as B, and this distance is sigma y. As I already explained, shear stress on top and bottom face is forming a clockwise couple like this, so it has to be taken as negative. Negative means it has to be drawn upward on the Mohr's plane. So I have to draw a vertical line at point B now, which should be of length tau xy. I will call this point as F, and the height of this line is tau xy. So I have marked the state of stress on the vertical faces with points A and E, and similarly the state of stress on the horizontal faces with the points B and F. Now the procedure is to join points E and F with a straight line. I am joining points E and F like this. And this line FE is intersecting the x-axis at a point like this. I am calling it as point C. Now you have to take a compass, and with C as center and CE or CF as radius, you have to draw a circle, and that is called as Mohr circle. I am drawing that circle now. This is called Mohr circle. Mohr circle. Now observe, circle has intersected x-axis at 2 points. Point P here and point Q here. Intersection of the circle with x-axis means those are the points where shear stress is 0. Because x-axis represents normal stress, on any point on x-axis shear stress should be 0. So P and Q are the points where shear stress is 0. That means Q and P are representing maximum normal stress where shear stress is 0, and they are called as principal stresses. So here the distance OP is actually sigma 1 maximum normal stress, and the distance OQ is sigma 2, which is called minimum normal stress or minor principal stress. But how do we find the orientation of principal planes? To do that, we have to consider the reference line. Here the line FCE is actually representing the given state of stress sigma x, sigma y and tau xy. So that has to be a reference line for us, or theta 0 position. So the line FCE represents theta is equal to 0. Now if I want the angle or orientation of major principal stress sigma 1, I have to measure the angle from FCE counterclockwise direction till the line OP, and this angle is 2 theta 1, from which you can calculate theta 1, the orientation of major principal plane. Then how do we measure 2 theta 2? We know that point Q is representing minor principal stress sigma 2. So I have to measure an angle from the reference FCE like this counterclockwise till the line OQ. This gives us a value of 2 theta 2, from which you can always calculate theta 2, the orientation of minor principal plane. So here the distance OP represents sigma 1, distance OQ represents sigma 2. If you want maximum shear stress tau max, you draw a vertical line at point C. Wherever it meets the circle, that distance will give you tau max. Here it is tau max. I will call this meeting point as H. Now CH is actually tau max. It is also radius of the circle. The angle corresponding to tau max can be calculated like this. This angle is 2 theta tau max. In order to calculate the normal and shear stress sigma theta and tau theta on a plane which is inclined at theta degree to vertical, you first calculate 2 theta. For example, if theta is given as 30 degree, 2 theta becomes 60 degree. So you have to measure 2 theta is equal to 60 degree from the reference line FCE and mark a point on the Mohr circle. Let us say 2 theta comes somewhere here. I am drawing a dotted line, and that line meets a circle at some point, and this angle is 2 theta. I will call this point of intersection of the dotted line with the circle as J. Now the coordinates of point J will give you normal stress and shear stress, because our x-axis is normal stress, y-axis is shear stress. So the distance of point J from tau axis will give you sigma theta, normal stress on the plane. Distance of point J above the x-axis will give you tau theta, shear stress on the plane. Don't forget one thing, tau theta, if it comes above the xy line, it has to be taken as negative. If you want to calculate resultant stress sigma R, join O to J. So here OJ is the resultant stress sigma R, which is actually the vector summation of sigma theta and tau theta. If you want the angle of obliquity phi, tan inverse of tau theta by sigma theta is here. So we have found out all the unknowns using Mohr circle method. This is a procedure for any problem in Mohr circle method. So we will try to apply this procedure for this problem, for which analytical solution is already available. In this problem, sigma x is minus 120, sigma y is minus 80, tau xy is minus 60, and theta is 180 minus 45, which is 135 degree. First draw a horizontal axis, normal stress, and draw a vertical axis, shear stress axis. Observe that I am keeping more space on the left side because my sigma x, sigma y, tau x all are negative values. So I need more space in the negative sigma axis. See, I have to represent all the values of sigma x, sigma y, tau x, everything in the space given. So I need to fix a proper scale based on the values. For this problem, you can fix a scale of 1 centimeter is equal to 20 megapascal. On the vertical face, you have sigma x of minus 120. Minus 120 is equal to 6 centimeters. So I am marking a point here at 6 centimeter distance from y-axis. That represents sigma x. So this is the point which represents the sigma x value. Now at that point, I should draw a shear stress of minus 60. Minus 60 is nothing but 3 centimeters. So I am measuring vertical line at that point, 3 centimeter distance. I have to draw it upward because shear stress is negative. I am marking a point there now like this. Next, you consider horizontal faces where you have a normal stress of sigma y, which is minus 80. Minus 80 is 4 centimeters. So measure 4 centimeters and mark a point there. So this point represents sigma y. At that point, I should mark a shear stress of plus 60, which is 3 centimeter downward. I got another point there like this. Now join these 2 points using a straight line like this. That is a reference line, and that line intersects the x-axis at the point which has to be considered as center of the Mohr circle. Now I have to take a compass and take this as a radius and center point and draw a circle. That circle is called as Mohr circle. We know that wherever this circle meets the x-axis, those are the points which represent zero shear stress or the planes of principal stress. This is one of the point where circle intersects the x-axis. This is another point where the circle is intersecting with the x-axis. If you measure the distance of this point from the y-axis, it is around 1.8 centimeter, which comes out to be minus 36 MPa, which is sigma 1, major principal stress. If you measure the other point, it comes out to be 8.2 centimeter, which is 164 megapascal, which is the magnitude of minor principal stress. To calculate maximum shear stress, you draw a vertical line passing through the center like this, and the length of that line will give you maximum shear stress. That is actually radius of the circle, which comes out to be 3.2 centimeter. 3.2 into 20 will give you 64 megapascal. Now we have to measure 2 theta 1, and I have told you that 2 theta 1 should be measured from the reference line like this. Observe, I am keeping the protractor, adjusting the protractor to align with the reference line, and measure the angle from the reference line till the principal stress 1. That will give you 2 theta 1. You will get a 2 theta 1 of approximately 71 degree. So theta 1 will be 71 by 2, which is 35.5 degree. Now we have to measure 2 theta 2, and 2 theta 2 is a large angle, so you have to measure the angle like this. So 180 plus this measurement will give you 2 theta, which comes out to be 180 plus 70. If you divide it by 2, you will get an angle of 125 degree. The same way, you can also measure the angle for the maximum shear stress. You keep the protractor like this, and this angle is actually minus 19 degree, or divided by 2 if you do, you will get minus 9.5 degree. Now we have to measure the normal and shear stress on an arbitrary plane with theta is equal to 135 degree or 2 theta is equal to 270 degree. 270 degree is nothing but 180 plus 90 degree like this, and you should get a point on the circle. Now measure the normal and shear stresses corresponding to the point of intersection of this line with the circle. If you measure, you will get sigma theta of 2 centimeter, which is minus 40 megapascal, and tau theta of minus 1 centimeter, which is 20 megapascal. We have obtained the solution now, but we have to mention the scale considered and name all the points and write all the values on the graph sheet. When we represent all the points and all the values including scale on the Mohr circle, it looks like this. Here Q is the point which represents major principal stress sigma 1, P is a point which represents minor principal stress sigma 2, A and B are the points which represent sigma x and sigma y respectively. AE represents minus tau xy and BF represents plus tau xy. Point C is the center of the Mohr circle. CJ or CE or CF will give you tau max value. You can also observe how 2 theta 1, 2 theta 2 and 2 theta tau max is measured like this. And the stress on arbitrary plane which is with inclination 2 theta is represented by the point J. Coordinates of point J are minus 40 and minus 20, which are nothing but sigma theta and tau theta. I will represent this in a separate page and explain again. This is sigma x, this is sigma y, and this is tau xy, and this is also tau xy. And using that, we obtain sigma 1 and sigma 2. Sigma 1 is this distance, this is sigma 1, and this is sigma 2. And if you want tau max, you have to draw a vertical line at point C. This is tau max. So this is sigma 1, this is tau xy, this is sigma y, this is sigma x, this is sigma 2, and this is tau xy. This angle is 2 theta 1. This angle is 2 theta tau max, and this angle is 2 theta 2. When you measure 270 degree from the line ECF counterclockwise and draw a radial line, it comes somewhere here. I'm calling that point as J, and the coordinates of point J, you measure it. This is tau theta and this is sigma theta. You can try this problem on your own. This is also solved analytically and you have the values. You better use graph sheets to solve such problems. I am using a graph sheet here. I know that sigma x is 42 here and sigma y is 40 MPa. Tau xy is 42 MPa. All are positive, so I can draw y-axis somewhere here, and I will draw the x-axis somewhere here. First I have to look for the vertical faces. Now in this problem, vertical face has sigma x of 42.4 MPa. So I will use a scale of 1 centimeter is equal to 5 megapascal here. So 42 MPa is around 8 centimeter. I will draw that on x-axis like this. This is the point. On the vertical face, tau xy is positive 42 MPa. So I am drawing it downward. On the horizontal faces, sigma y is 40 MPa. So 40 MPa normal stress will come somewhere here. On the same plane, shear stress is same value but in the opposite sign. So I have to draw it upward like this. I will get a point there also. Now you have to draw a straight line from these 2 points, and wherever that new line meets the x-axis, that is the center of the Mohr circle. Now that center as a radius, you draw a Mohr circle like this. I have to measure this distance now. This becomes sigma 1 and this distance will be sigma 2, and this distance, radius of the circle, is tau max. If you measure this angle, this becomes 2 theta 1, which gives you the orientation of major principal stress, and this angle will give you 2 theta 2, which gives the orientation of minor principal stress. This inclination gives you 2 theta tau max. In this problem, the plane is inclined at 30 degree, theta is 30 degree, so 2 theta is 60 degree. So if you measure 2 theta from the reference line, it comes somewhere here. You draw a radial line there from the center of the circle that meets the circle at this point, and the coordinates of that point, if you measure, that becomes normal stress and shear stress on the plane, sigma theta and tau theta. This is how Mohr circle is used to solve such problems. We can always compare these results with analytical results. If you take a proper scale and do the graphical construction accurately, you will be able to get comparable results. Now we will consider two specific cases. First one is Mohr circle for uniaxial loading. For example, a bar subjected to load like this, axial load. Here only sigma x is present, sigma y and tau xy are 0 here. When you try to draw the Mohr circle for this, this is x-axis and this will be y-axis. So this is sigma and this is tau, which is positive downwards. When I represent sigma x on x-axis, it comes somewhere here, let us say. Tau xy is 0 there, so I don't have to measure anything vertical there. Sigma y is 0 means it is the point where origin is. Using these 2 points, I have to draw the Mohr circle, means I will get a center somewhere here in between those 2 points, that is C, and draw the circle that will be tangential to the y-axis like this. Now this represents sigma x here. Now consider the second specific case, Mohr circle for pure shear. We normally come across a case of this kind where only shear stresses are present, normal stresses are 0. Here sigma x and sigma y are 0. If I try to draw a Mohr circle for this is y-axis, this is x-axis, here it is sigma and here it is tau. Here sigma x is 0, so you will get origin as starting point. Sigma y is also 0, but tau xy is present. One side it will be positive, one side will be negative, so you will get 2 points like this. So you will have to take origin as a center and draw a circle, and that becomes the Mohr circle like this. Like this, you can apply this method for solving any two-dimensional case. You can try to solve this problem using Mohr circle method as a homework. This is also solved analytically. You can compare the results of Mohr circle with the analytical solution.